All right, so this is the start of Module 13, and this module we're going to be talking about thermodynamics. We've briefly touched on this back at the very beginning. I think it was back in maybe Module 2, and we talked about energy. So this whole module is just going to be all about energy. I'm just going to talk about the three things we're going to talk about, and then we're going to start breaking it down. Okay, so the first thing we're going to be talking about is enthalpy. Okay. And we're going to be talking about this in two different ways. We're going to talk about bond energies, and we're going to talk about Hess's law. This is all under the canopy of the first law of thermodynamics. The second thing we're going to briefly talk about are energy diagrams. So basically pictures, what energy looks like as a picture without using numbers and words. And then the third thing we're going to talk about is entropy. So you're going to have to right away off the bat realize that enthalpy and entropy are two different things. They sound very much the same, but they are different. And entropy is talking about the second law of thermodynamics. So the first part, we're going to be talking about the first law, and we're talking about the second law. And in with the second law, we're going to be talking about Gibbs free energy. Okay, so that's just a quick overview, and now we're going to start diving into it. Okay, so remember back, we talked about energy, right? And we talked about how energy, it can't be created and it can't be destroyed. So really energy is just transferring, right? It's a give and take of energy, and we look to see where it goes and what happens to it, okay? So when we have a reaction happening, a chemical reaction, we can actually apply that same idea about energy that we first talked about to these chemical reactions. So let's start talking about enthalpy, okay? When we have a chemical reaction, so imagine this is our reaction symbol, and we've got our reactants and our products, okay, on either side. I didn't put them in here, but we'll get to that. We can either have energy be a product of the reaction, or it can be one of the reactants, okay? So, and this is what this is showing over here. If we have energy as an outcome, it's going to be one of the products. It's going to be found on this side of your equation. Now, if it's going to be one of the reactants, it's going to be found on this side. And all that really means is the energy is actually being pulled from the surroundings. It's another one of the reactants. Let's say you had a substance and oxygen in the air. Well, energy could also be considered something in the surroundings that is being used in the reaction, okay? And in this case, let's say we have our substances over here. The outcome of that reaction is going to be an increase in energy. It's going to be more energy formed, okay? So the first law of thermodynamics, like I said, says it can't be created or destroyed. So we're just going to be going back and forth in these reactions. So if I find energy as a product on this side, we know that it's going to be an exothermic reaction, okay? That means it's going to give off heat, okay? Because in terms of practicality, energy is like heat. You can think of it that way, okay? So if it's putting energy out into the environment, exo is out, you're increasing, because more energy means more movement of molecules means more heat, okay? Opposite is the endothermic. If you find energy and you're grabbing it from your surroundings for your reaction, it means you're taking that energy or that heat away from the surroundings, pulling it in to use it, which means there's an absence of heat, which means it actually cools it down, okay? So that's going to be an endothermic reaction, okay? Remember, chemical reactions don't really produce or consume energy. If it doesn't do that, where does the energy come from? Okay, so now this is where we start talking about potential energy and kinetic energy. We talked about it a little bit. Remember, potential energy is energy that is stored, and kinetic energy is just energy that's in motion, okay? So we can think of potential energy as the energy stored in the chemical bonds of a substance. So if I have carbon dioxide it's got a bond structure, right? That if I have potential energy, it's actually being stored in the bonds of the substance itself. Whereas kinetic energy is actually the energy that is the heat that is associated with the chemical reaction. So you could think of potential energy as the energy stored within bonds waiting to be used, and kinetic energy is the heat that's associated when it's released, okay? On page 418, if you look at it, you'll see examples of a chemical reaction, and then you'll see the word energy in red, okay? And this is basically what it's showing you. Energy can be added to the backside of a chemical reaction, whether it's one of the products or one of the reactants, okay? Let me move this over. Chemists have decided that enthalpy, remember enthalpy is just change in energy, okay, that it's going to be labeled with an H. Okay, that's just what they decided. So if I want to find the change in energy, this is what it's going to be, this is what it's going to look like. This is change in enthalpy, okay? Now, chemists have really shortened it. Instead of saying change in or change of, they just call it enthalpy. So when you hear enthalpy, you should be thinking it's the change. It's the change in the energy associated with that reaction, okay? So they're just going to kind of shorten that a lot. So if we solve for a delta H, or a change in enthalpy, we're looking to see what happened to the energy in this reaction as we ran it, okay? Now, if I run my equation, I'm going to show you that equation in just a minute. If I run my equation and I get an answer, a numerical answer that has a negative number, that tells me that it's exothermic, okay? And we're gonna walk through this in just a minute. That's what you can see it here. That's what this little negative symbol means. But if I run my equation here and I get a numeric answer with a positive number, that tells me right away that it was an endothermic reaction, okay? So this would tell me that it's going to get cold, and if I get a negative, that tells me it's going to be hot. Likewise, if I get a negative answer, I know that the energy is actually a product. It goes on this side of the reaction. But if I get a positive number, that tells me that the energy is actually a reactant from the surroundings, and it's going to be put on the reactant side to the left, okay? So that's what those positive and negatives mean right there. So let's just look at an example, and we can get the hang of this, okay? So we're on page 420. It says, when CH4 undergoes complete combustion, the change in enthalpy of the reaction is negative 803.1 kilojoules. Write a balanced chemical equation representing this process. Include energy in your equation. So the first thing we need to do is come together with an equation. We need to balance it, and then we need to figure out where energy goes, which side it goes on. So they said CH4, and they said it was complete combustion, so this should be easy to do by now. We know complete combustion requires O2. One of the products is carbon dioxide and water, okay? Now we need to go ahead and balance it. I'm not going to go through all the time. I'm just going to use the book to balance it faster so we don't waste a bunch of time. So this is my balanced chemical reaction. Now, the last thing they said is to include energy in your equation. They gave you what the energy outcome was. They said it was negative 803.1. So negative, according to my chart here, negative tells me that it's on the product side, and it's going to be exothermic. So this is really important. You don't just take that number and plop it there. The negative or positive symbol on the front end just tells you which side to put it on. Once you realize which side it goes on, you just take the number itself and put it there. So I'm not going to put negative 803.1 kilojoules. I'm just going to put 803 because it's not a negative outcome, right? It's energy. You're either going to have it on one side or another, okay? So over here on the end, I just put plus 803.1 kilojoule. I don't think you can see it. I'll have to move it over next time. So really you just tack it on to the end, okay? So your first on your own set, 13.1, you're going to do this, there's 3 of them, okay? So they're going to have you make the chemical equation, and then you're going to balance it, and then you're going to figure out which side. So if you look, the first one says negative 814. Well, according to what we learned, a negative is going to be on the product side. So you're going to put not the negative, you're just going to put positive 814 on the right-hand side. Look at the next one. It's a positive number now, 2,030 kilojoules. Positive numbers are endothermic, so they're part of the reactants. So you would put that number right at the end, okay? So go ahead and try that, and then we're going to move on. Okay, so now that you've done those first couple problems, you've gotten the hang of which side the energy goes on, okay? Now, we're going to actually talk about how did you get that numerical value. So they gave it to you for us, that delta H, the change in enthalpy or change in energy in the reaction. But there's actually 3 ways to find it, okay? The first way, we're just going to briefly touch on, okay? Because we did this way back, I think it was module 2. So the first way to do it is to actually run a chemical reaction by an experiment. So remember we made a calorimeter way back, I don't know, what is it, module 2? You guys didn't, but some of you might have. So if you run an experiment with the calorimeter and you basically isolate everything so that you can see just the change in the energy within that reaction, okay? So that's what that experiment, so if you go through this experiment on page 421 and 422, that's what you would find. That's what you're trying to do, okay? You're trying to solve for that delta H. So that's the first way. There's 2 other ways, and these are the ones we're going to focus on in this module, okay? So the second way to determine the delta H, the enthalpy of a reaction, is to use bond energies, okay? So you can see right here on my list, this is the first way. We can find bond energies. I'm going to walk through that in a second, okay? And there is another way. So here's the 2 ways. Here's my delta H. I can either use bond energies or I can use Hess's law, and we'll talk through both of these. So the second one is bond energies. Let's talk about that. So it should make sense that whenever you have a chemical reaction, really what's happening is you have your reactants, the substances of your reactants, they basically are going to break apart and rearrange themselves to form the products, right? Because we know when we have a balanced chemical equation, we don't lose any of those things. They have to balance. They just get rearranged, okay? So if you take a look at the Lewis structures on page 423, you can see that they broke down each one of those into the Lewis structures, okay? So that's what we're going to do for bond energies. We're going to break each molecule down into its Lewis structure to see what bonds are there, and then we're going to assign different values to those bonds, okay? So think about it this way. It takes energy to break something, right? If I've got something in my hand, I want to break it, I have to exert energy on it to break it. So on the reactant side, you have to expend energy to break those bonds, okay? But on the product side, when you rearrange those, those bonds, they form new products, right? Well, anytime a new product is formed, there's actually a release of energy. So you can think about it this way. It takes energy to break on the reactant side, and whenever you form a new bond, ta-da! There's a burst of energy, okay? It's like, yay, it's like the celebration of creating a new substance, okay? So that's how we're gonna view this. So let's see, go ahead and turn to page 424. You'll see a table of bond energies there. Oh, I think I got ahead of myself really quick. Okay, real quick. Let's say I have, so here's my reaction, here's my reactants and my products, okay? Let's